All right, so this is for the Argos Lab calorimetry of food, where we talk about heat, right? We talk about heat in Unit 1. We're not going to be using the formulas. Heat is equal to mass times specific heat times the change in temperature. We're going to use some temperature, change in temperatures, but there's something we call the response factor that we're going to be using to help us calculate heat, which is just a little bit easier for the lab. So background again, go ahead and read the background information here. This here, not necessarily going to be required, but just something you can read through. And we'll just jump into the you can read all of the introduction, take some notes there. And we'll start with the experiment. So the combustion chamber. So what we're doing is we're going to combust some alkane, right? Well, no, I'm sorry. We're going to combust aluminum in the presence of oxygen, so combustion reaction. So let me get this. Let me get some of the supplies down here. And it's asking us to do quite a bit of aluminum here. So 7 to 10 grams. So we'll just put the weigh boat in there, tear that out. And I'll just give it a walkthrough. You're going to be doing something similar to the for the unknowns, but for demonstration purposes, let me get started with this one here. So 7 to 10, so 1, 2, 3, 4, 5, 6, 7. And here we are. We're about 7 grams. So, let's put one in. It says 7 to 10. So even if you get a little over 7, it's perfectly fine. See that I have 8. It's between the 7 and 10 that they're requiring. And then I'm going to click in here, make sure I see that cursor, and then I'm going to hit record. Oop, didn't go. And there it is. Now recording my value. So we do need initial temperatures because we are doing a change in temperature, right? Our delta T, which is the max temperature that the graph is going to provide us from the experiment, and then our initial temperature. So do not forget to take this initial temperature here. I know that it's bouncing around a little bit, but it's okay. Just whatever value I see, and I see 23.38. So 23.38 is my initial. I'm going to go ahead and dump this in here. We're going to put this in the trash, and I can close that up, and we're now going to prepare to combust this. So uh, this reaction does take 3 minutes, so you do have to wait that, right? There's no way to speed it up. This will take 3 minutes. The unknown will take 3 minutes. The other unknown is going to take 3 minutes. But we do have to get some oxygen in here because we're going to combust this in the presence of oxygen. So we're going to open this up for about 10 seconds. If you go over the 10 seconds, it's perfectly fine. You just need to put in here enough oxygen, and we do that by 10 seconds at least. So you see that it's 14 seconds, perfectly fine. I'm going to hit this lever, and I've stopped it here. Now that we're ready, we're going to ignite this to combust that aluminum. And the combustion reaction will go, and you'll start seeing, there it is. It starts graphing this. I'm going to pause the video and resume it once this reaction takes place, but it is going to go for 180 seconds. Okay. So you see how we had this max incline here. The reaction should be almost over. We are getting there. But you'll see the high point. This analyze button is going to turn blue when we're ready to record the max or input the max temperature. Um, So you notice that there's no record button here, so we have to manually put that value in. But I'm trying to see the arc here because we're going to answer a question later on and see where it says 515. This is on the y-axis, so 515 degrees. But you'll notice when we analyze it, because now see there it is, it's turned blue. We analyze it 519.8. So we're going to input 519.8 degrees Celsius, which is higher, just a bit higher than the 515 that we see here. And now you're going to go ahead and do these for the same process. You're going to repeat that. Remember to reset this. The resetting, it'll clear all of that out. And then again, this value is in here already. It's not going to record a new value until you hit the record button again, and you'll get that for the unknown. So let's just go ahead and skip forward a little bit here. Those are our masses, initial temperatures, and then we get to our discussion where we're going to figure out the heat in kilojoules for aluminum. So um, when oxygen combusts in this reaction as well as or the aluminum combusts in the presence of oxygen. Oxygen releases some heat as well. We need to include that for the heat combust in kilojoules for the reaction. So in order to determine the heat combusted is we're going to take the mass of aluminum, and we do have that value recorded here. So the value I recorded was 8.0029. I'm going to put that value here and multiply it by this value here. So, right, AI burned in excess oxygen releases, or I'm sorry, aluminum burned in excess oxygen releases 31.1 kilojoules per gram. Um, how many kilojoules released during the combustion of your aluminum sample? And we're going to use this value here to determine what that calculation is in kilojoules. Now, the temperature change for aluminum, and we do have those initial final pressures, right? So make sure you're looking. It's going to be a little confusing here, but make sure you're looking at the right one. Here's the initial temperature. This is aluminum, initial temperature of aluminum, and we have the max temperature here. You're just going to subtract those two here. But remember, significant figures here. We're doing subtraction, which means we have to keep in line with the number of decimal places. Uh, this is 2 past the decimal. This is 1 past the decimal. To make sure our answer is at least 1 past the decimal place. And then we're going to calculate something we call the response factor, right? So using the measured temperature change of the calibration that we did with the aluminum, we can use that response factor to calculate heat generated by the unknowns. So what is this response factor here? So the response factor right here. So our response factor, RF, right? How we calculate that is the change in temperature over the heat combusted in kilojoules. And we do have, or we don't have it here, but those are previous calculations that we just talked about a minute ago, right? Uh, we have the temperature change and the kilojoules. So we're going to take that temperature change divided by that, and our answer will be in degrees Celsius per kilojoule. And that is our response factor. So this is not your response factor. This is just something I put in here, right? So let's say when I calculated this, the response factor is 3.0 degrees Celsius per kilojoule. Don't forget that we can also use this as the reciprocal value and put it in as kilojoules per 3 degrees Celsius. So that when we get to um, the unknowns, right? The unknowns here, well, if we can figure out what the temperature change is, once we know the temperature change, we can use it to calculate the kilojoules, right? And we're going to set it up like this. So here, this portion here is for the unknown. We're going to use the reciprocal value of the response factor, which is going to be in kilojoules over the degrees Celsius. And we're going to multiply that by the temperature change. So the degrees Celsius cancels out, and our answer is going to simply just be in kilojoules. So you'll note that for both unknown 1 and unknown 2. And when we talk about the energy content of the unknown, so the heat of combustion of the unknown, we just divide the heat combustion, which was previously calculated here. Here's the heat combustion here in this calculation. If we divide that by the mass of the unknown, that is the energy content in that first unknown. And you repeat that process for unknown number 2. So why is it important to collect temperature data over time rather than using the maximum temperature displayed on the calorimeter readout? Simply the maximum of their temperature was not the projected max. Remember I mentioned that? Um, So due to drift, some heat losses, the program estimates what that max should have been, right? Remember, it was just a few degrees off there, like 515 to 519 when we actually analyzed it. So there's just a little bit of heat loss in there. So the program just estimates what that max is going to be. And this will finish off the calorimetry lab.